Okay, so firstly, again, thank you all for attending today's talk. And so today I'm primarily going to discuss a general overview about the aspect of thin film interface engineering, especially focusing more towards condensed matter physics topics. That's where I come from. So the overall theme of my talk is going to give you a perspective of how thin film research is interesting towards condensed matter, and so in that sense, I'm primarily covering an overview of the research activity that's being done in my lab without going in great detail of the physics being carried out. But so before I start, I would especially like to acknowledge all our lab members. They are like our collaborators, internal collaborators, especially our students Saurabh, Satyaki, Suman, and Archit. And postdocs Joy, and also Dhawla Suri, who's joined us recently. And in terms of collaborators, yes, the results that I'm going to share are also in collaboration with Tanushree Sadasgupta from SN Bose, Indra Dasgupta from ISSS, and the student Shubhadeep. So, and regarding funding, yes, it's very important that our activity continues, and we are generously being supported by TFRDA and also from our extramural SCRB grants. So with this, let me come to the main theme. So I think all of us are aware of the technology around us, the digital age that we call, is primarily started many decades ago, and the starting element in some sense has been this material. This is bulk crystals of silicon. And we spent lots of effort in terms of purifying the silicon, and there's interesting growth methods starting from a seed layer to be able to build these single crystal ingots from molten silicon, especially highly pure molten silicon, by controlling various parameters such as pulling rate and all those things. And this is something we are all familiar with when we talk about silicon technology. So you see here, these are essentially bulk crystals. So the question is, how do you really make devices? And that's where people started off making these ingots and then slicing them and finally making these.
Excuse me, Kartik, your slide is not moving and it's also not in presentation mode, looks like.
Okay, 1 second. Let me do it again. Let me share it again. Let me do the entire screen. That's easy because sometimes it doesn't work that way. Now, is it moving?
Yes. Yes. Yeah.
Okay. So even this slide did not come, right? Acknowledgement side didn't show up. Can you see the acknowledgement slide?
Yeah. Now it is moving.
Okay, fine. Okay. Yeah. Okay, sorry. So yeah, I think acknowledgements were for my students and postdocs in the lab and also our collaborators. So yeah, when you talk about bulk silicon ingots, so these are primarily made using techniques that we are familiar with in terms of bulk crystal growth. But when you want to make devices, we often use these ingots and we slice them using a diamond blade, and we make wafers out of them. And this wafer is what is typically called silicon wafers of various diameters that we use extensively for our device fabrications. And this is what has driven the thin film technology. You use these wafers, you build devices on it, especially MOSFETs, active passive devices, and all these things essentially goes down into your small IC chip, which we call, which is part of a motherboard. And these chips, which exist almost in every instruments around us, has driven the technology forward. And all this is possible based on the concept of thin film technology. So, so just a little perspective. So when we started off with silicon, we always wanted to improve our performance, computing power efficiencies. And we always followed the concept of Moore's law, which basically tells you that every 18 months, the number of transistors that you can put in a certain square inch or a specific area is just doubles every 18 months. And this is something that we have followed over the years, over many decades. But we are reaching a limit where this is really not anymore possible. But in approaching the current technology, we've kind of adopted various new strategies. For example, conventionally, we started off with just using silicon, boron, phosphor, as dopants and started off making the devices. But now if you look at the actual devices technology nodes that people at industries like Global Foundries, Intel, IBM working on, they use even rare earth materials from the periodic table to be able to build these MOSFETs with very high on-off ratios. And talking about technology node, so currently, for example, we started off many decades ago from a technology node of almost 1,000 nanometers, 512 nanometers, and slowly we have come down to a range where we talk about the pitch of our die, which is used in the fab industries, is around 5 nanometers. That's what right now Intel and Global Foundries are aiming for. And what that basically means, we're talking about distance between the source and drain electrode to be of the order of 5 nanometers. And that's a huge challenge in terms of controlling the gate, controlling the channel just below the gate. And there have been improvements, like you have a concept of wraparound gate, where you put a better gate on 3 sides and gives you better control of your channel through the source and drain. And we've also moved towards the other technologies, is bottom-up, where you start with a nanowire and then you wrap around the gate and then you use that as a dielectric medium to primarily have a better on-off, better control on your transfer properties. So this is what has driven the roadmaps of typical VLSI technologies over many decades. But the question is, what next? And this is where all of us are right now, essentially, trying to figure out what's the best way forward. And if you look, what we're trying to do is, try to solve problems of nature by using these devices, or using these technologies. And an apt quote from Richard Feynman a long time back is perfect for this scenario, which is that nature isn't classical, and if you want to make a simulation of nature, you would better make it quantum mechanical. And that's simply because it's a wonderful problem and it's also not so easy to solve. And if you see, that's what is pushing now our technology, our research program towards the quantum technologies and quantum computing. And we don't know how the field evolves and how the things go in maybe next 20 years. So just to give you a philosophical understanding of the things around us, we talked about the digital age. And the digital age is primarily what we see around us, our laptops, smartphones. All of them are primarily driven by this logical operations of zeros and ones. And this is logical also from our perspective, because when we think of any question or any problems, it's like, it's always a logical answer of a yes and no. And that's why it started off with a logical problem defining 0 and 1, and all the algorithms that we see even in technology, silicon technology developed, is based on essentially such a concept. And therefore, our brains are also wired. As you grow from a childhood, our brain is also wired to answer a question in a logical way. But what we have done in doing so is that, if you see, this is a block sphere, and if I say my 0 state is the north pole and the 1 is my south pole, we have confined all our logical operations along this red line, along only primarily a single line. But if I tell you that it is possible to develop states, it is possible to develop technologies which could exploit the possibility to be in any possible combination of 0 and 1, or essentially anywhere on the surface of the sphere, and that state can be used for performing quantum operations, or performing logical operations, or performing actual processing tasks. And that is what drives the quantum technology, quantum era. And as you can see, because you have infinite number of possible combinations, you can primarily do exponentially faster computing with this. And going ahead, we don't know how our kids will respond, because if the kids are really exposed to quantum device which thinks quantum mechanically, it could be very well that our brains are wired in a different way, and even the questions asked might be very different, and perhaps we start thinking quantum mechanically. So this is a bigger picture that that is driving this field forward, and we are essentially trying to perform basic research activities in this subject. So, as I gave you an example of what we call as silicon technology, and that was driven by essentially by the bulk crystals of silicon. But now, if in the quantum age, we're talking about different kind of materials, and these materials, which we call as quantum materials, are primarily made of exotic materials, mostly chalconized and telluride system that I've shown here. especially selenites and tellurides. So these, as you can see here, these are all macroscopically bulk-like systems, but still we call them quantum materials. And the reason is that there's some property, macroscopic property of these, which essentially are showing quantum mechanical response. This could be, for example, quantization of Hall response in your bulk crystals, or various other reasons, such as you have dissipation-less transport, which is somewhat cannot be explained primarily classically, but quantum mechanically it gives rise to its extremely high transport without dissipation. And a perfect example of this is essentially topological insulator. So if you take an example of certain materials, such as bismuth selenide, antimony telluride, bismuth telluride, so these are materials which are essentially bulk they are insulators in the bulk. That means they don't conduct any electrons in the bulk, and so they can be considered essentially not contributing to any transport. But at the surface of these materials, it so happens you can have a very highly conducting flow of electrons. And they are not ordinary conductors. They have very interesting properties, which I'll come to in the next slide. But these conductors especially have very can flow without much of dissipation. And to give you an analogy, this is essentially an example. This is basically a few slides made by my students. I think it was very helpful. So what you see here is that an ordinary conductor. If I equate or tell you that if we assume that these motorbikes or cars are just like electrons flowing their material, and you can see they are very diffusive, and they constantly change path because they're kind of interacting, and essentially gives rise to dissipative transport. But imagine a scenario where you're on a highway, where the flow of electrons is just not hindered, and it just continuously flows without any dissipation, and it's highly mobile. Even if it encounters a defect like this, for example, it channels itself around it and again gets connected back. So these are very interesting topics of analogy of what you expect at the surface of topological insulators. And this is what we are trying to now explore in thin film forms. So just to give you a little flavor of why these things really happen. So these are primarily driven by the electronic states of matter, the concept of electronic states of matter. So if I take a normal insulator, we all know that normal insulator electrons don't really propagate. And you could assume as if you have a nucleus of your atom and the electrons revolve around the nucleus and they are confined. And such insulators can be defined electronically in terms of a band gap. So you have valence band, conduction band, you have large band gap, and these insulators don't contribute. But if you take another scenario where you have highly mobile, highly conducting two-dimensional materials, and you apply an out-of-plane magnetic field to the system. And if you apply out-of-plane magnetic field, you essentially you force your electrons to enter into a cyclotron orbit. And if the orbit time, time that the electron takes to orbit is much less than the typical relaxation time of your material, electron relaxation time in the material, that means the electron is primarily trapped in this orbit forever, and it cannot conduct in the bulk. So you are turning essentially a material into an insulator by applying a very high field out of the plane. But at the edges, if you see here, at the edges, they are not able to complete the path, and these are called skipping orbits, and these skipping orbits gives rise to a specific flow of electron only in one direction, which is what is expressed electronically in terms of band structure by an edge state, which can only propagate from left to right in this case, and other way around from the right to left. So these are the primary two systems that we have been aware of from a long time. And if you see here how we have converted a system from a nicely metallic system or a semiconductor system to an insulating system is by applying field. So you break what is called the time reversal symmetry of your material. Now there's a concept that can you achieve such states without really applying any field to your system or without breaking the time reversal symmetry? And that's where this famous model, kagome-lattice model in 2005, where it predicted that the internal spin orbit interaction, the spin orbit field within the material can be considered to be as an internal field, which can give rise to such edge state formations. And how that happens is because you essentially create this band inversion because of spin orbit. And this band inversion then interacts and have interaction with the bands, which primarily opens up a gap. But at the surface of these materials, you create these linear dispersive bands. And these are called essentially surface states in the case of a 3D topological insulator, or in the case of a 2D insulators, these are essentially edge states. So this is what is primarily driving us right now towards the concept of moving from two-dimensional systems to three-dimensional systems. And a three-dimensional quantum insulator or a three-dimensional insulator is just based on this concept. So just to give you a classification of why is it, what do you mean by topological insulators? So if I can give you a very simple analogy, which is if you take a two-dimensional material, I told you here that the edge states have skipping modes, and they are primarily as if they have states within the gap. But states within the gap could be of different kinds. For example, you can have states which are like this, which are basically, because you have spin-orbit coupling, it essentially causes a splitting in the momentum space of your up and down spins. But this is what you can expect. One possibility is you would expect the edge states to be like this, or it could be in the form of intersecting edge states. Now, these two, if you go into details of understanding the electronic properties in the momentum space of the systems, you can define that this is a conventional insulator. It's an ordinary insulator with an ordinary edge state, and these are special insulators, which are topological insulators, and you cannot transform your band structure from left to right or right to left. And the analogy is given very similar to a sphere and a donut. If you have a sphere, whatever you do, you deform in any way, unless until you poke a hole, you cannot enter into a donut state or into a coffee mug state, which also has a single hole. So this is a typical analogy, which is saying that you are in a system which is topologically invariant or topologically non-trivial. And this non-trivial essentially means that whenever you want to go from one state to other state, you need to close the gap. And that's why you have the formation of these edge states in your system. And without going much into details, it's just a small slide, again, just describing that what happens when you have the electrons in your band. This you could model by a simple box equation, which is given by this expression here. And if you try to look at the simple Schrodinger's equation, and you try to assume now, if I take an electron here, and I let it propagate over a space, say C, or contour C, and it completes the closed path, I can see that typically an electron can also acquire a phase as it propagates over a contour. And this phase has two components. One is dynamic phase, which just depends on how the energy changes over a period over the contour, or it actually has a curvature dependent effect, which gets essentially added up, giving rise to a Berry phase. It's called a Berry phase, which essentially takes into account the contour that the electron maps over the momentum space. So this is what is an additional property which is non-trivial for such materials. And they are essentially called topological Berry phase concepts, which is essentially driving the field of topological band theory. So this was just the basic flavor of explaining how these materials have very different electronic properties, which have so far not been exploited. And it's only in the last decade that things have really rolled out, and experimentally especially, and people are probing these materials. So the question now is, how do we make these materials? How do we make devices out of it? So I'm showing you here on the top is a bulk single crystal of bismuth selenide. Okay, and so this is something interesting. Just I showed you like a silicon ingot. But how do you kind of go beyond? If you want to make thin film devices of these materials, is a challenging concept. And that's where we use this system called a molecular beam epitaxy system, which essentially takes the elements of, say, in this case, bismuth and selenium. We co-evaporate them. We control the flux ratios of the two. And in ultra-clean environments of ultra-high vacuum, which is typically -9 or below, we grow these materials at specific temperatures, and we in situ can also look at the quality of these, the growth of these films. So this is a concept of epitaxy, which forces the films that you're growing onto a substrate and forces the films to have a lattice constant which is different from its own bulk values, but takes up the values corresponding to what is there on the substrate, and therefore introduces concepts of strain and everything. So this is what we primarily do. We have these cases which primarily go inside here, and these contain the elements which is now used to grow these materials. So what you see here is primarily the kind of lab which helps us kind of look at these, or helps us grow these materials. So this is just an image of what we have in our lab, which is essentially a combination of different vacuum chambers, which are just interconnected together. So you have right now an MB, you have a sputtering system, which are connected. So you could essentially make your devices using different techniques. And as I explained to you about the concept of heterostructure, which is primarily the fact that we want to control or engineer the strain that we produce in our films. As I mentioned here, by growing epitaxially, you can actually play with the strain of your film. And once you introduce strain, essentially, you change atomic spacing, you change the band structure, you change a lot of things in terms of how the films respond. And these modulations can help you sometimes give you, sometimes help you in getting better electronic, optical, and magnetic responses. So our goal here is to primarily engineer strain, stabilize the new phase, which may not be possible in the bulk. And when you talk about heterostructures, we look at proximity effect studies in terms of what happens when you bring in two different materials, two dissimilar materials with different interesting. One could be purely driven by electronic, one could be purely driven by a magnetic response. And if you bring them together, what really happens at the interface? So these are the concepts that we kind of look at. And it is interesting because these are all, once we demonstrate certain physics, it's always technologically scalable to the next level. So just to give you an example, if we can grow layer A and say an RMB system, then you can move it to a sputtering system, grow layer B without essentially contaminating the surface. It's all in an ultra high vacuum. We move the sample to sputtering. And if you want to look at the properties, say at the surface of B, we could actually even move it to the STM in situ and try to probe the properties of the surfaces. This is something just recently we got everything connected together, and we are right now in the mode of kind of testing and looking at properties of quantum materials. And we can even actually study these fields or samples in fields, perpendicular anomaly field, which is looking at the magnetic transport measurements. And we can also have a small ion milling system, which is a very small area one. It's a very small beam current. But this also helps us in terms of patterning our devices into different structures, like bulbar structure in this case, and then look at properties of systems. So I probably, in the interest of, I haven't really timed myself, but I'll probably only touch upon the first two topics, and the last I just kept it in case I have some time. Otherwise, I'll just skip the last talk and come to the conclusion. Okay, so we're talking about topological insulator. They're primarily different kind of materials. What we have worked on is bismuth selenide and recently bismuth telluride. So these are materials which are basically consist of these quintuple layers, which is basically a layered of bismuth and selenium. And between these two quintuple layers, which is both ending with selenium, so there is a van der Waals coupling between two selenium layers, and therefore each quintuple layer is somewhat unique. It's to the system, and this three quintuple layers is what forms a single unit cell of your system. So this is an example of the films that were grown in our lab, where these are bismuth selenide grown on Seeker sapphire substrates. And you could clearly see here nice layered growth of the bismuth selenide films. Obviously, because of the strain, you see a different intensity of a cross-sectional image. But you can also see we can actually grow them layer by layer, even on amorphous substrate, which is silicon oxide. And this is primarily gives very good control right down to, in fact, few monolayers, where we can optimize the growth and the transport of the systems. So in terms of the characterization, so this is an in situ technique where while growing the film, you could actually look at diffraction pattern being formed on your phosphorescent screen. And this is what you expect, basically. You basically are looking at 2D arrangement of your atoms on the surface. And if I have an electron beam, which is a grazing incidence, this is called reflective high energy electron diffraction. They get diffracted from the two-dimensional surface and gives you the various diffraction spots, which you can capture here. Typically, you expect to see a line. A line essentially defines how two-dimensional your surface really is. And the spacing between these two can help you actually back calculate the typical lattice constant in plane arrangement of the atoms and the typical lattice constant of the system. So what you see here is for epitaxial systems is you will see they typically need to have a, in this case here, 6-fold symmetry. So if you rotate your sample from 0 degree in plane rotation of phi, if you rotate your sample, you can go from a structure, from a pattern like this to a pattern which is double spacing, and then it gets back at 60 degrees, you get back the same pattern. So that's a confirmation that you are actually going epitaxially, and you have essentially looking at growth, which is don't require really XRD to really confirm the epitaxial nature of films. Okay, so why are we doing this? So we are first of all studying these materials to probe surface properties of such materials, which looks very similar to graphene, which is you create primarily a Dirac cone state at the surface. So you have 6 surfaces, so you have 6 Dirac cones. And if you look at the dispersion, they are again very similar to graphene, they are linear dispersive. And they are very interesting properties, as I mentioned earlier. You have pi Berry phase, you have spin moment blocking, and you have a Dirac point, which is similar to graphene. Now, what we wanted to look, or what we are probing in one of the projects in our lab is to look at the proximity effect studies of the surface with a magnetic insulator. So we are coupling the electronic properties of bismuth selenide with the magnetic properties of a proximatized material called europium sulfide, which is essentially a ferromagnetic insulator. It doesn't conduct electrons, but it has a magnetic moment. And we're trying to see how does this moment couple to the surface state of the bismuth selenide, in some sense the Dirac cone. And now the theory tells you is that if you have a localized moment generated in your surface state, you can open up a gap. And this gap opening is not a trivial gap opening, but it's essentially a topologically non-trivial band gap, energy gap opening, which gives rise to exotic effects, such as in this case, half integer or quantum anomalous Hall effect, where you start seeing a Hall response of the order of E square by 2h, which is what we have shown here. Okay, so this is the physics in terms of what we expect, which is called the anomalous quantum Hall effect. And not just that, but has very interesting responses also if you go into a little bit more detail, which is, I told you here, I've put only ferromagnetic US only on one side of the surface. If you could put on 2 sides of the tops or bottom side surface of your topological insulator, and then you apply field to your system, you can actually drive your system into 2 exotic quantum states. One is quantum anomalous Hall insulator, where you see a gap opens only in bottom and top surface, but on the edges, you still have very good flow of electrons. You have dissipation-less flow of electrons. These are essentially currents that can flow without any dissipation. But if you go to an antiparallel state of your top and bottom ferromagnetic insulator, you enter into what is called an axion insulator state, where you open up a gap even on the side edges. So it's a perfect insulator. So you can go from a conducting system to a perfect insulating system just by changing the configuration of your ferromagnetic layers. And one could use this, for example, as a sensor. For example, if you have stray fields which can switch to orientation, then you can go from a high resistance to a low resistance state. And this is primarily some of the basic device applications one can really think of. Okay, now the property of EUS and bismuth selenide is studied in the past, especially if you look at the growth of EUS lithium sulfide, which is called an Heisenberg ferromagnet. That means it's driven by the concept of Heisenberg exchange, but it is electronically insulating. What it tells you is that when you grow this EUS, when you are high temperature, you force these moments of EUS to be out of the plane of your film. But as you go down in temperature, they kind of cant, and they cant inwards into the plane. And this is what is seen from a typical squid measurements. So we started analyzing these things from thin film format from our lab, where we grow these materials, the bismuth selenide, for example, and we grow essentially also the magnetic insulator on top. So this is a typical plot of how the resistance of your device looks as you cool down in temperature. You have metallic response. At low temperatures, you have kind of flattening with a small upturn, which is visible here, which has various reasons. I don't want to go into detail here, but these are primarily coming because of kind of 2D localization of your films. So we characterize these materials heavily in terms of the thickness to optimize the fact that, for example, for our 16 nanometers, is more or less metallic with slight upturn. and this is heavily consistent and observed in our samples. But once we grow europium sulfide on top of it, for comparison, this is a reference sample, and as soon as you grow europium sulfide, you see a strong upturn. You have a strong metal to insulator transition that is occurring in the device. And if you look at the mobility response, it's very much similar. So though the mobility remains very similar, you see a strong transition from a metallic or a gradual upturn response to a strong upturn response. That tells you that at the interface between business cell and EOS, there's something that is happening giving rise to such a temperature-independent metal transition. This even for the different thicknesses of our films. So how to characterize them? So we did some gate-dependent studies. In fact, we changed the gate voltage, which helps you to kind of look at changing the carrier concentration in your topological insulator film. And what you observe is that if you see here at 0 voltage, gate voltage, you have a conventional response of this upturn which I showed you. But when you apply positive gate voltage, you see a sudden drop in resistance and then a hump and finally goes up. And you also see this film becoming more and more metallic in nature because you see a downward shift in the resistance of the film. More importantly, this particular gate voltage, where primarily you are increasing the carrier concentration at the top interface between the bismuth selenide and the EOS, you see this sharp resistance drop, and you see this increase in the temperature at which this upturn in resistance happens. If I do the same measurement, say at 50 volt, and I do a measurement of while cooling down and warming up, you see a clear difference in the response. You have a small hysteresis appearing at around 19 Kelvin, which is close to the bulk TC of EOS, and you have another one appearing at around 32, 33 Kelvin, which is essentially tells you that when you apply gate voltage, you can induce carriers in your film, conduction electrons, and these conduction electrons kind of interact with the europium atoms. So if I tell you this simple picture, if you have europium atoms which are localized spins, and you generate these surface electrons, which are highly conducting, and they can couple and give rise to an indirect exchange between the two localized 4F or spin states of your europium atoms. And this exchange coupling essentially gives rise to an enhancement in the Curie temperature of europium sulfide. And this tells you one of the first predictions, one of the first results confirming that there is indeed an RKKY type interaction that exists in business and EOS interface. And primarily we have more results in it, but for this talk, the focus has been primarily to tell you that these interfaces can give rise to very interesting effects. And we also primarily confirm this response also in the fact that this such responses not at all seen in our reference devices, which doesn't have europium sulfide. Okay, so the RKKY interactions is somewhat interesting. This is just summarizing our work, which is published in Quantum Materials, which is also in agreement with the recent, with the previous theoretical work where they predicted indeed that you could actually induce indirect exchange through the surfaces of the TI to give rise to an enhanced exchange interactions in the europium sulfide material. So this is primarily covers the first part of my session. So if you have any talks, I can take right away. Otherwise, I'll just move on to the next topic.
Yeah, I have a question. How from your reverse, forward and reverse variations, you see that there is a very less loss or hysteresis loop in this result. So what makes it so stable?
What makes it more stable in the sense,
or less low loss? Does it show there is a loss or something else in the loop that you are getting?
the loop
R versus
okay,
temperature?
no, so this primarily happens because if you look, the EOS material typically is a magnetic moment. So when you suppose, let's say when you're cooling down, when you're cooling down, typically the moments, the domains of EOS are randomly oriented. And if you look at that perspective, the domains are so random that they actually don't contribute to strongly to the exchange response, because there are multiple domains, they all cancel out to each other. And that's why the response is weaker. and then when you cool down, finally the domains grow in size. And once they grow in size, you essentially end up into a scenario like this. But now when you warm it up, you're already in a scenario where the domains are larger in size.
Okay.
And therefore this is typical around the phase transitions, ferromagnetic phase transitions, where you do expect an hysteresis to open up, primarily because driven by this variations in the domain size. So because of this variation domain size, which affects in the transport measurements also, that you give rise to such hysteresis roofs, especially around the place where you have Curie temperatures be forming. So what you observe is at this temperature, you essentially have only the interface, which is coupling with the conduction electrons having a higher TC, shows up.
Okay.
And as you go here, at this temperature, the bulk EUS, which is farther away from the conduction electrons or anything being influenced, they have its own TC, bulk TC, which starts picking up, and therefore you see a different curvature showing up here. So you have two humps. One is you have a change in slope, which you can see here very clearly.
Right.
You have two humps.
Okay. And is there any, what is the time between the measurement that you take between two temperature reading? Is it instant measurement, or there is a delay, because material will have some kind of relaxation and
yeah. So typically these are done in a cryostat. So the sample is very nicely thermally anchored to your probe with a copper block. So it's always the case that the typical time frame is, I would say each temperature point variation is around, because we wait for temperatures to stabilize, so it's around a minute.
Okay.
So,
Thank you.
Thank you. If there are no other questions, let me just move on to our second topic, which is essentially talking about Weyl fermion physics in kagome-lattice antiferromagnetic systems. So what's a Weyl fermion? So the Weyl fermion is again driven from the concept of condensed matter physics, driven by the topological bands theory, which tells you that when you have high spin materials, in certain specific classes of materials, especially which break the concept of time reversal symmetry or inversion symmetry, one could expect to form these Weyl-like excitations in your band structure. And these Weyl fermions are nothing but fermions which are linearly dispersive, just like your graphene, except that you have these two Dirac cones which are shifted in momentum space, and they don't appear at the same point. So these are called, instead of Dirac points, they are called Weyl points or Weyl nodes. When these two merge together, you essentially end up into a 3D Dirac material. So there is a degeneracy of your Dirac point in a 3D Dirac material, which you can lift by breaking the time reversal symmetry or the inversion symmetry, giving rise to a shift in the momentum space of these Weyl nodes. And therefore, you associate a left chirality to the one node and right chirality to the second Weyl node. And there are chirality-driven effects that often appear in these systems. And one could essentially do band structure calculations for such materials. We essentially end up into seeing band structures like this, where around the Fermi level, especially in this case, you can create Weyl points, which are linear dispersive bands. And in terms of the Berry phase, that phase that the electron acquires, I mentioned before, which is essentially also similar to Berry curvature, you will see that there is a sharp rise of Berry curvature, changeover in Berry curvature exactly at the Weyl node. That is again an indication that you essentially have created a non-trivial electronic responses around these points. And these excitations are nothing but similar Weyl excitations, which is driven from the concepts of high energy physics. So yeah, so essentially this again the concept is similar. You have band inversion, you have hybridization, and that gives rise to in a three-dimensional. So the graphene is primarily a two-dimensional material. I talk about momentum space in 2 dimensions. If you extend the concept of three-dimensional momentum space, in three-dimensional momentum space, somewhere in the three-dimensional momentum plot, you will expect linear dispersive bands appearing, which replicate or which represent the excitations observed in typical Weyl fermion systems. Now, kagome materials are very interesting materials because these are essentially nothing but lattice structures consisting of triangular and hexagonal units, as you can see. And these are primarily very spin systems which are very frustrated. If you see, if I associate an antiferromatic exchange between the neighboring atoms, these two know how they must align, but the third one really doesn't know how to align. And therefore, in that sense, they are geometrically frustrated. And this frustration can introduce very exotic, non-collinear ground states of these material structures. You could even observe chiral systems, especially when there is an competitive interactions in terms of exchange and other intrinsic, what is called the Danish-Moria interactions. So we are primarily talking about a system called Mn3Pt, so which is a manganese 3 platinum system, which is a cubic structured system. If you take a 111 plane of this system, which is what is shown here, the 111 plane of Mn3Pt, you can see here these are nothing but atoms of manganese arranged in a Kagome network, and these are centered by certain platinum atoms, which are high spin orbit materials essentially. If you see here, if you see this triangle, the spins are all out aligned. In this case, they are aligned inwards. So this is basically called an all-in, all-out spin configuration of Mn3Pt. And this is highly non-collinear. It gives rise to very interesting Berry curvature effects, which are kind of not describing much in detail here, which is giving rise to interesting anomalous Hall signals. But to give you in terms of the flavor, how we grow these materials, so we use this sputtering here. So we primarily use targets of platinum and manganese, and we co-sputter them. So this is done in our in-house kind of, we design our own chambers. So one of the things that we do in our lab is primarily all these things that you see primarily designed by us in terms of how to align the targets. And this is not commercially available. So this is a turret style sputtering system where you can do co-sputtering with least contamination. Co-contamination is very limited. And this is where our samples reside. So this is how we typically make our films. We check the quality of the films with XRD and with SEM to confirm the stoichiometry of our films. And so the XRD shows very interesting epitaxial growth of Mn3Pt, which is confirmed from XRD out of plane and also from the phi scan, which tells you that you have fourfold symmetry of your substrate and your film peaks appearing, telling you that indeed you have large grains at least, and they are epitaxially oriented on your sample. More interesting, what you observe is that you can create strain. You create a strain in almost around 2% strain in the Mn3Pt film. From the electronic responses, they are heavily metallic. They are highly metallic. They have very large resistivity ratio, which is basically the ratio from the room temperature to the base temperature. So that tells you how good the quality of your films are. And these are primarily structurally strained systems. So one concept that typically tells you or helps in terms of analyzing or confirming that you have a presence really of Weyl fermions is this concept of chiral anomaly. Now we know that when you apply magnetic field to your system, you typically localize your electrons. So you always generally within the localization framework, you always observe positive magnetic resistance. That is, when you apply magnetic field to your system, the resistance always goes up. And this is true irrespective of how you apply a field. Maybe there'll be anisotropy in terms of the percentage of MR magnetic resistance that you observe. But it's always the case in most systems, the resistance always goes up when you apply field. But chiral anomaly is different because if you have Weyl Semimetal phase, which is shown by essentially linear dispersive bands, and you apply field to your system, and the field is applied, say, in the X direction here, shown here, and you also apply your voltage in the same direction as your applied field, then what you could do is you could drive your current, your electrons, chiral currents, from one band, chirality band, to the other chirality band, representing the other Weyl node. And in this way, you populate, because in these systems, the chirality is conserved, the electrons from one chirality is very difficult for it to scatter back to the other chirality. It's a long, reaction times are very long. So as a result, you essentially populate one electron one chirality band more over the other. So you can create holes here, you create more electrons here. And this means that when you apply magnetic field and current in the same direction, you are able to generate extra current or reduce the resistance of your device. And this is essentially negative magnetic resistance. You reduce resistance of your device when you apply magnetic field. And this is heavily angle sensitive. Any small deviation from I parallel to B or J parallel to H, you will observe that you will start seeing positive MR. And this is what is shown here. I've shown device configuration here, where you can essentially do a measurement of your resistance RXX by changing the field in both theta and phi plane. So if I take the phi equal to 0 plane, that is XZ plane, and apply a field from out of plane 90 degrees to in plane, I see the positive MR rapidly goes down, and you see negative MR appearing at 0. At phi, again, it starts slightly going up, whereas 0 is exactly negative all throughout. You repeat the same experiment for in-plane measurements. Because of in-plane measurements, you essentially rotate the field in plane. So you've taken a 0 degree, which is negative MR. You rotate it such that your I and your J and H are not parallel anymore. So you are 10 degrees, 90 degrees. You again start seeing positive MR appearing. So this is a very sensitive, angle-sensitive measurement that is possible to confirm that indeed you have the presence of Weyl fermion systems. And this is also confirmed with the collaborators with the DFT calculations, which again shows you that you have formation of these Weyl points around these, what is called the M symmetry points in your Brillouin zone. And not just that, they are very other exotic, interesting fermionic system, which is more in detail in terms of condensed matter physics. So this is primarily where we are, and I'll just slide over maybe next 5 minutes in terms of our also efforts in terms of understanding a new concept, a molecular strain pulley concept in the area of molecular spintronics. So we all know when you put molecules on a very inert surface, we assume that the interactions are van der Waals driven. And so we always model a system where the molecules essentially takes up energy states which is slightly broadened because of its interaction with a metallic system. But you can still observe discrete energy states of your molecules, which is also shown here. But imagine you have a system which is a ferromagnet, which is essentially very reactive, which has the spin split D bands. And now when they interact with the molecule, you can create a strong hybridization effects. And these hybridizations give rise to very interesting interface properties, which are very, very different compared to your starting material, which is a molecule or a ferromagnet. You have essentially interface states, which gives rise to interesting properties when you try to measure any current or perform any measurements in field. How do you observe this? Is basically do a spin contrast spectroscopy measurements, where you essentially observe that if you put the molecule on top of a ferromagnet, you can essentially probe this in terms of contrast of how the electron spins change as you go over the molecule. This is a surface of iron, which is having a negative spin polarization, for example. And as you move over the molecule, you end up into a positive polarization. That means the density of the spin states, the spin contrast up minus down, is reversed as you go over the molecule. So these are essentially the techniques that is used to confirm or to look at the strong, what is called the chemisorption, the strong hybridization effects of a molecule on the surface of ferromagnet. We looked at primarily one effect, which is the surface magnetic hardening effect, which tells you that when you put the molecule on the surface of a ferromagnet, you can actually increase what is called the coercivity or the switching field of the ferromagnet. You can make it harder. And this again is interesting because hard magnets are technologically very superior in terms of their applications. And there's one thing that is already being proposed in various proposals where one could use this hybrid ferromagnet molecule heterostructure or assemblies to be able to increase the coercivity of the ferromagnets that can also reach all the order of few Teslas. So now talking about one effect, which is the exchange bias effect, which is what I'm going to quickly go over, which is that if you have a ferromagnet, we know that it has switching field, which is symmetric around zero field. But now which can be measured using this anisotropy magnetic resistance measurement called AMR. But now if I put a hard layer, and I put a hard layer in proximity to this material, I can essentially switch the hysteresis loop to one side, because there is a spring action that develops across the interface, which forces the ferromagnets to have a shift in the hysteresis response and also in the AMR. And this is, as I mentioned, is primarily driven by the spring-like action that appears across the interface, which could also happen if you have an antiferromagnet at the bottom. And interestingly, when you thin down the antiferromagnet, you thin down the antiferromagnet, the anisotropy kind of reduces, and you primarily weaken the exchange bias effect, and you kind of kill the shift in the hysteresis. But with molecules, we actually observe the other way around. So I'll just skip this thing. So what we have done is that we have grown the molecule, say manganese tyrosine molecule, on a surface of iron. Okay, so we have two samples. One is without the molecule, which is a reference sample, and one is with the molecule on top, the iron, and we are capping it with aluminum, which is helping in terms of preventing any oxidation of the system. And we do a standard measurement. So this is the dip in the AMR here that you see here is a representation of the cohesivity or a switching field. So what you observe is that when we have reference iron, blue one, it primarily is very flat. But the molecule one picks up, and around below 100 Kelvin, it really shoots up, and the cohesivity of switching field really goes up. And this is driven primarily, as I mentioned, because of the chemical nature of the interaction between the molecule and there's a hybridization, giving rise to what is called the magnetic hardening effect. But more interesting, what we observe is that the hardening can be so strong that you start observing very interesting effects. For example, you cool down your film at low temperature, 1.5 Kelvin, and you do a hysteresis measurement. You don't see essentially any hysteresis appearing. It's a very back and forth without any hysteresis. It just keeps repeating. But when you go to a larger field range, you start observing hysteresis. And this is essentially shifted. So if you see this center point is not zero. It is shifted by a large amount. And this is essentially the exchange bias effect. Now, this is interesting because you put just one monolayer of your molecule on the surface of iron, you still observe this effect. And we call this essentially exchange bias effect. So what we have done in doing so is that we have primarily been able to drive the response of our film by decoupling the iron such that the surface iron has an independent magnetic response compared to bulk. The surface switches, or the surface is hardened because of interaction molecule. It is the bulk that switches independently of your surface. There is an exchange effect. That's why it gives rise to spring-like action, and you have an exchange bias response observed here. So I just want to conclude here by saying that summarizing the results here is that you have this, we call this as a molecular grain Fourier effect, which basically tells you that if you start high temperature, you put the molecule on top, you have essentially a response which is given with black line, which is nothing but a mix or a average of response of your bulk ion and the surface ion, which has a very high cohesivity. But at some low temperatures, the surface layer becomes magnetically stable. In a way, it becomes so hard that it's able to stabilize independently and have a very high switching field, whereas the bulk starts switching with a lower field and gives rise to what is called the exchange bias effect, as we observe in our devices. So with this, I just want to conclude and again thank them all for the contributions. And yeah, so this is something I just want to end up saying, that we do help other institutions in terms of the support for growth, thin film growth, and also in terms of other vacuum technology products. So with this, I would end, and I would have to take any questions.
Thank you very much, Kartik, for the very interesting talk and showing us the quantum way all the way. And now the floor is open for the question. Please, either you can type or you can ask by unmuting yourself. Yes,
To
yes,
Kartik,
Ram.
when is it likely that these such researches in the country would lead to the development of a device? Do we have the foundries at hand other than SCL? And they are not, I guess, open to you as well to even fabricate the device that you have developed you in these labs.
Agreed. Yeah. So the right now it's a long way to go. There is a lot of initiative in terms of money being pumped, at least on paper. But yeah, the other thing is that the conventional device foundry is again built primarily for silicon, as what I mentioned. So the silicon age is kind of ending. So even the foundries that exist are primarily can only do silicon-based processing. That's one of the reasons like companies like IBM really sold off all their foundries, because they do realize that in the coming years, we need to move beyond silicon. And also the reason why now they're heavily investing in quantum computing, quantum materials, quantum technologies. So the existing foundries, I don't think have a solution. The other thing is that no, unlike the case of silicon, where you kind of evolved. At the end, we are doing this silicon technology, improving the computational power is all because we want to solve simple problems like solving the full electronic structure of caffeine, or understanding how caffeine really affects the body. Those things right now we can't even model with our existing computational resources. But with quantum computer, even if you have say 100 qubit or a 1000 qubit chip, you can do many things which is beyond existing conventional technology. So this is an open question in terms of foundry, but I don't think it will be as capital intensive like it is for silicon.
Thank you.
Thank you.
I have one question. Why is this edge effect very important? Is it because of the size? The edge effect that you shown in the first topic.
Sorry, first results you're talking about, which one?
In the edge effect itself, that you were showing that that changes the state, edge state, I think you mentioned over there.
The edge states, okay.
Yes.
Was a result or the introduction side?
No, interpretation, like why it is so important in these particular devices or material. Is it because of the size, or it is
Okay.
like?
So it's interesting is because so these are the examples. So edge states. So these are essentially states. So if I tell you like this, so example, let me just show here. This is easy to explain. 1 second. I'm sorry, where did it go? So let's take this edge state here. And this is drawn by this dispersion moment. Okay. So now if I tell you that if I have an electron which is here, now this electron here can only propagate in one direction. It cannot go back.
Okay.
So if it sees any impurities, it needs to be backscattered. Right. So an impurity will essentially scatter the electron. And if it scatters the electron, eventually you can say it's like there's a probability of backscattering. But it can backscatter only if there is an available state in the negative momentum path. But there is no state available for it to back propagate. And therefore, these are systems where even if you have impurities, they will just go around the impurity without getting deflected or without essentially affecting its velocity or momentum. And it will still propagate dissipationless. They will not exchange any energy with the system and propagate dissipationless. So it's like a highway where the electrons can flow easily with high mobilities. And that's one of the reasons why the dissipation is less, which is one of the major concerns right now in the silicon technology or in existing technology, where the amount of heat that you generate at your core is almost touching essentially the heat generated at the core of the sun in terms of power density.
Okay, thank you. And the setup that you shown, can we do, so everything you mentioned that everything can be done like using, let us say, through one chamber, right?
Yeah.
Like a sputtering, then characterization using TM and all can be done just by inserting your device in one chamber, right?
Yes. So we can, in principle, make the full device stack without exposing it in air.
Okay.
This is important, especially because like in silicon technology, you have these clean room fabs where after every step you take it out, you do lithography, then you coat the next element, or you essentially do implantation, and this
Yeah,
is
right.
what we're doing. But when you talk about spin rated response or newer condensed matter devices or even quantum devices that people are making, all of them primarily needs to be done where the active region of a device, where all physics happens, cannot really at any time be exposed to air. So with that intention, this is where we make sure that all the interfaces, which is what drives our physics, is clean, gives you reproducible results. And once the full pattern is made, then you can pattern it, you can take it out, you can do the required patterning and make a device geometry, because this nowhere exposes the interfaces as it does in a conventional fab.
Right. Thank you. Now, is there any other question? All right. Mr. Ramamurthy Garu, you want to ask?
No.
Okay.
Thank you. He's already answered.
Okay. Okay. Okay, Kartik, since there
Thank
is no
you so much.
question, thank you so much for your time
Yeah, thank you so
and
much.
the interesting talk. Thanks a lot.
Thank you.